Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is Module 21 in my Computer Networks lecture series where I talk about routing algorithms. Now, we're coming to the end of our discussion of Layer 3, and we have by now talked a lot about the concept of routing tables. We've introduced the idea of routing tables, and we've done a very specific example where we created a Linux routing, or the routing tables necessary to network a series of Linux computers together. And that exercise was done manually. Basically, as humans, we looked at the physical map of a network, we saw where we had routers, and we created the routing tables by hand necessary for packets to flow across that particular network. However, the internet, in general, routing tables on the internet are not created by hand. It would be impossible. So what we're going to talk about in this module are the algorithms, which we refer to as routing algorithms, the algorithms that automatically populate the routing tables used by all the routers across the internet. And there are a variety of different routing protocols out there. We're going to look in a little bit of detail at kind of a venerable example called the Routing Information Protocol, or RIP. RIP is still out there. It's one of the older algorithms, though. There are definitely a number of newer ones. But I like RIP because it does illustrate kind of some of the quintessential properties of routing algorithms that make the internet so successful. And so I've said a number of times in this lecture series that there is no sort of centralized node with global network knowledge, calculating routing tables and, sending those routing tables out to the different routers. The routers themselves figure out the tables they need to basically just using local information, local knowledge. So by exchanging messages with their immediate neighbors. And somehow this just chatting with your neighbors approach to creating routing tables still does successfully create routing tables that allow packets to travel globally across the internet. So somehow a bunch of Canadian routers just chatting amongst themselves can create routing tables that make it possible to send packets all the way across the world, Australia, Europe, Asia, wherever we want to go. And so at the heart of the example algorithm we're going to be considering, which is RIP, at the heart of RIP is a technique called the Bellman-Ford algorithm. And we're going to focus very specifically on the Bellman-Ford algorithm because it's going to show us how local information can be used to create a globally successful series of routing tables. So if we look at the Bellman-Ford algorithm in a little bit more detail, it's basically an algorithm for finding the shortest path through a graph. And often, as we've said a few different times now, often there are potentially a few different paths that a packet can take through a mesh algorithm. So if we have a source node communicating with a series of routers, on its way to the destination, obviously the packet can either go this way or the packet can go this way to reach its destination. Now, which way should it take? What's the shortest path? Well, it does seem like this top path is the shortest in terms of hops, right? Because there's only 3 hops to get to the destination, whereas, to go through the bottom path, there would be 4 hops. However, not all hops are necessarily created equal. In some cases, we will have links that have a higher throughput, than other links. Maybe there's a link that corresponds to a high-speed fiber optic link and another link that corresponds to maybe a lower speed sort of copper Ethernet kind of link. And so we need to take that into account. So basically, the Bellman-Ford algorithm will do that for us. Now, the Bellman-Ford algorithm is based on this notion that we can represent a network as a graph. And a graph is essentially just a series of vertices, or a series of dots, which we call vertices, that are connected by lines that we refer to as edges. And so this should be a pretty comfortable looking picture. You know, this is basically exactly the way we've been drawing mesh networks up until now, where the nodes on our network would be our vertices, and the connections between our nodes, the communication links, would be our edges. And so the Bellman-Ford algorithm was originally developed in the area of what's known as graph theory. But graph theories, many of the ideas developed as part of graph theory are now used as part of network design, because graphs can so easily be used to represent networks. And one idea central to the Bellman-Ford algorithm is that each of the edges, each of the links in the graph, are given a cost value. And basically, the cost value can be used to represent how good the link is for carrying data traffic. So, for example, we might give a cost of 4 to this link, but maybe only a cost of 2 to this link and a cost of 1 to that link. And so the lower the cost, basically the better the link is for carrying information. So it would basically essentially be the inverse of throughput, for example. So a very, very high throughput link, a nice clean fiber optic link, high-speed Ethernet, would have a low cost. But if the link was had a lower data rate, then it would have a higher cost. Also, you could imagine the cost of a link being adjusted dynamically based on traffic. So if a link was experiencing a lot of congestion, a lot of packets, then its cost would go up, whereas a link that was relatively quiet could perhaps reduce its cost in order for traffic to kind of dynamically flow from higher, more congested areas of the network to lower congested areas of the network. Okay, so the best way to learn how the Bellman-Ford algorithm works is through an example. And let's consider the following network map or graph as what we're going to use for our example. And we can think of this, the vertices or the nodes on this graph, perhaps as representing routers in a big sort of high-speed backbone network. So for example, if we're looking inside an autonomous system and we're looking at the big routers connected by high-speed links that maybe network cities together, those could be represented by these nodes. And so, each of these nodes would have like a bunch of smaller links branching off of them, to serve the subnets in their institutions or in their cities. And so our objective will be to illustrate how the Bellman-Ford algorithm is used to populate routing tables. So we're going to assume that we have a network where all of these routers are turned on and nobody knows how to reach anybody. So the routing tables are completely blank, and we're going to use the Bellman-Ford algorithm to populate the routing tables. Now, if we were going to, normally the routing tables would have entries that would allow any node to reach any other node. So for example, node 5 would have routing table entries that would tell it how to reach nodes 1, 2, 4, 3, and 6. Node 6 would have entries that would tell it how to reach nodes 1, 2, 3, 4, and 5. However, we're going to kind of simplify things a little bit, and we're just going to focus on the routing table entry that allows the nodes to reach node 6. So we're essentially just going to look at how we create one single routing table entry. So that'll be our objective. Forward to create for reaching node 6. And you'll notice in this example that we have costs associated with each of our links, and the costs are not all the same. So this link has a cost of 1, this link has a cost of 2. And again, we can think of the higher cost links as being a little bit worse for carrying traffic. So no, the link with a cost of 1 is maybe a nice high-speed link with very little traffic on it, and the link with a cost value of 2 might be a slightly slower link or a link that has a little bit more traffic on it. So it's going to take a longer time to deliver our packet. Now, the purpose of the Bellman-Ford algorithm, as I said, is to find the minimum cost or the shortest path through the network. So when we take these costs into account, the minimum cost path or the lowest cost path for node 2 to reach node 6 is through node 4 and then node 3. So if we traverse this link, we have a cost of 1. Through this link, we have a cost of 2. And through this link, we have a cost of 1. So the total cost for that link is equal to 4. You will note that it's also possible for node 2 to reach node 6 via node 5. This route has a smaller number of hops. It's only 2 hops. But because these are higher cost links, the total cost for this path is equal to 6. Right? So the Bellman-Ford algorithm, when we associate different costs to the links, we'll always choose the lowest cost path, not necessarily the path with the fewest number of hops. However, if we did want to use the algorithm for finding the path with the fewest number of hops, the way you do that is you just assign all links in your network the same cost. So give all the links a cost of 1, basically, and Bellman-Ford will find you the minimum hop path. So to start things off, I want to make a few general statements about the Bellman-Ford algorithm, introduce some general notation, and then we're going to dive into our specific example, and you'll see very quickly how things all sort of fit together. But to start off, I'm going to use a particular notation for a routing table entry. Oops. Change my pen color here. So each routing table entry I'm going to use represent by 2 numbers in round brackets. The first number is D and the second number is C. So this first number is the next hop on the path to node 6. Remember, this example is very specifically on how to reach node 6. The second number, C, is the total cost to reach node 6. So the routing table entries will keep track of not only the next hop to the destination, but also the total cost to reach the destination. And we'll see how this kind of works into things. So what if we have no information on how to reach a node? So for example, what if we just turn our router on, our routing table is totally blank. What do we put in our tables if we have no information? Well, there is a default that we use to initialize our routing tables. So for the first number, we put in a dummy or a garbage address. So -1 represents just we have no idea what the next hop to node 6 is. And for the total cost, we initialize that to infinity, or practically speaking, a really, really large number, the maximum number of whatever number system we happen to be using. So if we have no idea how to reach node 6, let's say after we first turn on our router, we will put in a dummy address for the next hop because we don't know which of the devices we're connected to we should use to send our packet. And we put in a total cost of infinity because we're very pessimistic, I guess. Maybe the cost to reach node 6 is infinite because we have no idea what the path is. But as we're going to see, initializing to this value is really important when the Bellman-Ford algorithm starts to operate. So another aspect of the Bellman-Ford algorithm is it's important for a node to have a table or an entry in its own routing table that represents how to reach itself, which seems like it's kind of silly, but again, this is an important aspect of the algorithm. So for example, node 6 would have the following entry on how to reach itself. So if node 6 wants to send a packet to itself, the next hop address is 6, right? It uses its own address. And the total cost of sending a packet to itself is 0. And so when the node 6 router is turned on, it has no idea how to reach anybody else, but at least it knows how to reach itself. And so at the very least, it can put one entry in the routing table saying, if I wanted to send a packet to myself, I would use my own address and my cost would be 0. As a bit of terminology, I'm going to be referring to iterations of the Bellman-Ford algorithm. And an iteration is basically a period of time where each router shares information with its immediate neighbors. Specifically, each router is going to share its routing table or its routing information with its neighbors. So now let's say that we're a router and we're talking with our neighbors, And let's say neighbor K says that it can reach node 6 with a certain cost. So if neighbor K can reach node 6 with a cost of CP, then our routing table entry would be K, neighbor K as our next hop, and then the total cost to reach node 6 would be however much it's costing our neighbor to send the packet to node 6, plus however much it costs us to reach our neighbor. So said another way, we know, so if neighbor K tells us that it knows how to reach node 6 with a cost of CP, we know that we can give our packet to that neighbor, and then that neighbor can then somehow magically deliver the packet to node 6. And so it's perfectly valid for us to say our next hop is to just give the packet to the neighbor, because the neighbor told us it has a path to node 6. And then our cost is equal to whatever it's going to cost the neighbor plus whatever it costs us to get the packet to that neighbor. And then finally, we only update our routing table entries with a new, with sending a packet to a neighbor if doing so lowers the cost of us reaching node 6. So we only update a routing table entry if the result gives us a lower cost than what we already have. Okay, and so that's how Bellman-Ford works in a very general, kind of abstract way. You might still be thinking, well, I kind of understand what he's saying, but I don't really. So what we're going to do now is we're going to work very slowly through our example, and by the time we're done the example, this will make a lot more sense. Okay, so here is our network. This is just the network that I had on the previous slide shown here so we can kind of look at it while we do our example. And here's a little table that represents the routing table entries in all 6 of our nodes. And again, all of these entries represent how each of these nodes are going to send a packet to node 6. So we're only really looking at one routing table entry per node. And we're basically going to work through 4 iterations of our algorithms. And again, an iteration is where each router shares its routing information with its immediate neighbors. Okay, so in iteration 0, basically we can imagine the network has, we've just commissioned this network and we turn all the nodes on all at once and they're all blank. Nobody knows how to reach node 6. And so our first table entry is going to look like this. Now, there's a couple things to note here. Basically, every single one of the nodes in the table, nodes 1 through 5, have initialized their routing table to the default entry. So the address -1 indicates that they don't have a next hop path to node 6. They don't know where to send their packets, and their cost is infinity. This is true for all the nodes, except of course for node 6. Node 6 knows how to reach itself, and so it initializes its routing table entry with its own address as the next hop and its cost as 0. So this is kind of, the stage I guess now is set. For iteration 1, all of the nodes are going to communicate with their immediate neighbors. And we're going to see what happens here. So the routing table starts to change. So but the routing table only changes for some of the nodes. So for example, node 1 didn't change. And so node 1 is over here in the network, and it basically says, hey, node 3, do you know how to reach node 6? And node 3, which we assume at the start of the iteration uses its old routing, it hasn't updated its routing table yet. Node 3 says, nope, I don't. And then node 1 says, hey, node 4, what about you? And node 4 says, nope, I don't know how to reach node 6. And node 1 then asks node 2, hey, node 2, do you know how to reach node 6? And node 2 goes, nope, I have no idea. And so node 1 goes, I guess nobody knows how to reach node 6, so I'm not going to update my routing table. So that's why node 1 didn't change. It's the same for node 2. Node 2 asks all its neighbors, hey, do you know how to reach node 6? They don't know. Node 4 asks nodes 3, 5, 1, and 2. They don't know either. However, it's a little bit different for node 3 and 5. Node 3 says, hey, node 4, do you know how to reach node 6? Node 4 says, nope. Node 3, just a little line here. Node 3 then says, hey, node 1, do you know how to reach node 6? Node 1 says, nope. And then node 3 says, okay, well, I guess I have one more neighbor to ask. Node 6, do you know how to reach node 6? And node 6 goes, yeah, that's me. And node 3 says, oh, okay, great. What's the total cost of reaching you? And node 6 goes 0. And then node 3 says, the cost, so I just had a neighbor tell me that they can reach node 6. In fact, of course, node 6 is that neighbor. And my neighbor says it can reach node 6 with a cost of 0. My cost for reaching that neighbor is 1. And so that means my total cost is going to be 1 plus 0, or 1. And then node 3 takes a look at its current routing table entry and says, wow, currently my cost for reaching node 6 is infinity. A total cost of 1 is a lot less than infinity, so I'm going to update my routing table. Remember, we only update our routing table entries when our cost is lower. And so, just to clean up my diagram a little bit here, node 3 changes its next hop entry to an address of 6, right? Because that was the neighbor that told node 3 that it could reach node 6. In this case, obviously, it is node 6. And the total cost of reaching node 6 with that direct transmission is equal to 1. Similarly, if we take a look at the situation with node 5, the same thing happens to node 5. Node 5 asks for, and 2, if they know how to reach node 6, those nodes say no. But then node 5 asks node 6, and node 6 says, yeah, I am node 6. I can reach myself with a cost of 0. And node 5 says, great. My cost for reaching you is 2. 2 plus 0 gives me a total cost of 2. That's a lot less than infinity, so I'm updating my routing table as well. And so after our first iteration, we have 2 routing tables change. And you'll notice, just kind of by convention in this example, we assume that this new updated routing table entry is not stored in the iteration, or not stored in the routing table until the end of the iteration. So, for example, at the start of iteration 1, node 1 asks node 3 if it can reach node 6, And node 3, when communicating with its neighbors, uses its old routing table information and doesn't update its routing table until the end of the iteration. So that's why we don't have this kind of instantaneous propagation. Hopefully that's clear. Okay, so that is the end of iteration number 1. Now let's move on to iteration number 2. For iteration number 2, let's take a look at what hasn't changed. So first of all, the entry for node 6 hasn't changed. The entry for node 6 has a cost of 0. You're never ever going to get lower than a cost of 0. So the routing table entry is never going to get updated for node 6. The routing table entry for node 5 has also not changed. So at the start of iteration number 2, node 5 is still going to ask its neighbors about whether or not they can reach node 6. So node 5 will ask node 4, hey, can you reach node 6? Node 4 says nope. Node 5 will ask node 2 if it can reach node 6. Node 2 says nope. And so node 5 doesn't change its entry. Same thing for node 3. Node 3 will communicate with node 4 and node 1. Neither of those two nodes know how to reach node 6 at this point, and so node 3's entry will stay the same as well. However, there are going to be some nodes that do update their routing table entries. So for example, node 1 is going to ask node 2, hey, do you know how to reach node 6? Node 2 will say nope. Ask node 4. Node 4 will say nope. But then node 1 is going to ask node 3, and node 3 is going to say, yeah, actually I can reach node 6 with a cost of 1. Node 1 says, great. I currently have a cost of infinity, and my cost to reach you, neighbor number 3, is 2. And so if I update my routing table entry, I'll go from a cost of infinity to a cost of 2 plus the total cost of 1 that node 3 is reporting. And so node 1 is going to update its routing table entry to send a packet to node 3 for a total cost of 2, which is its link cost, plus a cost of 1, which is what is being reported by node 3. By the same token, node number 2 is going to ask neighbor number 1, hey, do you know how to reach node 6? Neighbor number 1 is going to say nope. It'll ask neighbor 4. Neighbor number 4 will also say nope. Then it asks neighbor 5, hey, neighbor 5, do you know how to reach node 6? And node 5 will say, yeah, I can reach node 6 with a cost of 2. So node 2 says, great, I can reach you with a cost of 4. And node 2 updates its routing table to send its packets to node 5 with a total cost of 4, which is its link cost, plus 2, which is the total cost being reported by node 5. And so we can see actually at the end of this third iteration that now we all nodes have a way to reach node 6. So they've gone from not knowing how to get to node 6 to every single one having a viable path. And at this point, hopefully you can kind of see sort of the magic of the Bellman-Ford algorithm. So it basically starts out with nobody knowing how to reach node 6 except for node 6. Then as neighbors start to share information, the knowledge of how to reach node 6 spreads from 6 to node 3 and to node 5. And then once And then in the next iteration, when nodes 3 and 5 share their information with their immediate neighbors, now all of a sudden everybody knows how to reach node 6. And so basically we are able to construct routing tables with global network knowledge just by neighbors sort of telling other neighbors what they know about their kind of immediate vicinity in the network. The last thing I want to talk about before we move on to the next iteration is what happens with node 4, because node 4 has kind of an interesting choice to make. So at the start of iteration number 2, node 4 is going to ask node 2, hey, do you know how to reach node 6? Node 2 is going to say nope. Node 4 will ask node 1. Node 1 will say nope. Then node 4 is going to ask node 3. Node 3 says, yeah, I can reach node 6 with a cost of 1. And then node 4 asks node 5, and node 5 says, yeah, I can also reach node 6, but my cost is 2. So node 4 has 2 viable paths to reach node 6. How does it decide? It basically, of course, chooses the lower cost option. Because node 3 is reporting a lower total cost, node 4 is going to choose to send its packet to node 3. And its cost is going to be 2 plus 1, or 3. And I should say that the decision that node 4 makes is based on its total cost. So the cost not only of what node 3 is reporting, but also what it costs for node 4 to reach node 3. So node 4 will make its decision on a cost of 2 plus 1 for this path versus a cost of 3 plus 2 for this path. Hopefully that's clear. So the total cost for node 4 to go through node 5 would be 5. The total cost for node 4 to go through node 3 is 3, so we choose node 3. So now every node has a viable path to node 6, and we can say, well, let's stop here. But as it turns out, the routing table is actually going to change one more time, or it's going to change in one place in the following iteration. And so at the start of iteration 3, we still have a local neighbor exchange. So even though we have a valid routing table entry, neighbors are still going to keep talking to neighbors, basically. And node 3 is going to, for example, say, hey, node 1, can you reach node 6? And node 1 will say, yeah, I sure can. I reach node 6 by sending packets to you for a total cost of 3. Node 3 will then ask node 4, hey, can you reach node 6? And node 4 will say, yep, I also send packets to you with a total cost of 3. And then node 3 will say, hey, node 6, can I still send packets to you? And node 6 will say, yeah, you can, and the total cost to send it directly to me is 0. And so node 3 will say, okay, I'm still going to send my packets to node 6 directly with a total cost of 1, which is just my link cost. So even though these routing, and the reason why I wanted to go through that is because even though these routing tables aren't changing, there's been an intentional choice not to change them. So node 3 is still exchanging information with all of its neighbors and assessing the situation and deciding, no, the entry table that I have is still a good one. And that's actually going to be true for all nodes in our network except for one. So all of our nodes are going to sort of exchange information with their neighbors and realize that their network, their current routing table entry is the best, all except for node number 2. So node number 2 at the start of iteration 3 is going to say, hey, node number 1, can you reach node 6? And node 1 will say, yeah, I can, and my total cost is 3. And node 2 will say, okay, my cost to reach you is 3, so that's going to be a total cost of 6. My current routing table cost is equal to 6, so there's really no reason for me to change. So node 2 wouldn't update to send through node number 1. It'll then ask node number 5, hey, node number 5, can you still reach node 6 with a cost of 2? And node number 5 will say, yep, that's still the case. And so node 2 will say, okay, well that is a total cost of still 4 plus 2 for 6. And then finally, node number 2 will ask node number 4, hey, node number 4, can you reach node number 6? And node number 4 will say, yeah, I can. And my total cost is 3. And node number 2 will say, oh, okay, your total cost is 3. My cost to reach you is only 1, so that's a total cost of 4. That's lower than my current total cost of 6. And so node number 2 updates its routing table entry to go through node number 4 for a total cost of 4. And so all the other routing table entries remained the same, except node number 2 did update, was the only one to update. And so that concludes the example. Hopefully now, after very slowly working through each one of these cases, you can kind of see how the Bellman-Ford algorithm works. Again, I love this example because it shows the magic of distributed networking. So there's no sort of global master entity that is using this map to determine these routing tables. These routing tables are getting created just based on information exchange between local immediate neighbors. Because information is only exchanged with neighbors, it does take some time for the information to propagate through the network. And so we've seen that in this example. We start out with a situation where nobody knows anything, right? That was what we initialized with. And it does take some time before we kind of work our way down this table and get to the point where everybody has the minimum cost path to reach node 6. But by the time we get to node 3, every packet that travels through this network destined for node 6 will take the minimum cost path. Now, the cool thing about the Bellman-Ford algorithm is that it can also adapt to changes in the network. So the RIP protocol will require, even though the network seems stable, it will require periodic updates where neighbors exchange information. And so let's say, for example, that node number 4 experienced some sort of catastrophic failure, a power outage or a processor burned out or something like that, or there was a fire in a server room, and node number 4 completely disappeared. What would happen then in our next neighbor exchange is that the cost to reach node 4 would all of a sudden jump to infinity, right? If we're not getting a reply from a node, the cost jumps to infinity. And so what would happen is after node 4 burns out, node 2, if it can't reach node number 4, would update the cost of going through node 4 to infinity. And then it would ask the other neighbors, hey neighbors, can you still reach node 6? And node 5 would say, yep, I can still reach node 6 with a cost of 2. And node 2 would say, okay, the total cost then is 2 plus 4 or 6. 6 is a lot less than infinity, and so it would go back to sending its packets through node 5 for a total cost of 6. And so that's the benefit of periodically updating the routing tables. And this is also why the internet is so easy to scale, because the routing algorithms are constantly exchanging information with their neighbors. It's no problem if a node disappears, But it's also no problem if we add another node. So for example, we could add a node number 7 to the network, maybe with a cost of 2 and maybe with a cost of 1. And node 3 and node 6 would start to exchange local information with their new neighbor, and information about node 7 would then propagate throughout the network, and routing table entries would be created for it as well.